Have you ever wondered how engineers figure out the work done by a swirling wind on a turbine? Or how physicists can possibly model a satellite's path through a crazy gravitational field? Well, you are in exactly the right place. Today, we're unlocking the powerful tool that makes all of that possible, the line integral. We all learned it back in physics class, right? Work equals force times distance. Simple enough, but here's the catch. That only works if you're pushing a box in a perfectly straight line with a perfectly constant force. The real world, though, it's messy. Forces change, paths curve. So what do we do when things get complicated? I want you to picture a kite caught in a gusty, swirling wind. The force of that wind is different at every single point, and that kite is definitely not flying straight. Trying to calculate the total work the wind does on the kite with our old formula, it feels pretty much impossible. This is exactly the kind of problem that line integrals were born to solve. And here it is, our hero for the day, the line integral. It's designed to handle something called a vector field, which, is just a fancy way of saying a space where every point has a force attached to it, kind of like our windy day. This integral lets us add up all the teeny tiny pushes and pulls of that force field along any curved path, giving us one precise number for the total work done. Now, what's really cool is that the answer you get is super intuitive. If the work, W, ends up being positive, it just means the force was helping the object move. Think of it like a tailwind. If it's negative, the force was fighting the motion, like a headwind. And if the work is zero, that means the force was always pushing at a right angle to the direction of motion, so it wasn't helping or hurting at all. Okay, so we get what it represents. But how do we go from that intimidating-looking integral to an actual number? Well, the key isn't to memorize some monster formula. Nope. Instead, it's about following a clear, step-by-step recipe that's going to work every single time. And here it is, our four-step recipe. First, we parameterize the path. All that means is we write an equation that traces out the curve over time. Second, we find the velocity vector by taking a derivative. This tells us which way we're going at any moment. Third, we evaluate the force field on the path. This tells us which way the force is pushing at each point along our journey. And finally, step 4, we combine those two vectors using a dot product and integrate. That last step is the magic that adds it all up. All right, talk is cheap. Let's put this recipe into action. And we're going to start with a tricky one, just to show you how powerful this method really is. We are going to calculate the work done by a force field on a particle as it zips along a twisting helix. So let's follow our recipe. Step 1, parameterize, is actually already given to us. That's our r of t. For step 2, we find the velocity by taking the derivative of r of t, which you can see right there. Now for step 3, and this part is absolutely crucial. We evaluate the force field F on the path. Since F is z, x, y, and our path's coordinates are cos t, sin t, t, we just plug them in. So z becomes t, x becomes cosine t, and y becomes sine t. And there you have it, our two key vectors all set up. Now for the first part of step 4, the dot product. This operation is basically asking a question at every single point. How much are the force and the velocity pointing in the same direction? If they're perfectly aligned, you get a big number. If they're opposed, you get a negative one. We just multiply the matching components and add them all up, and we get this single function that perfectly captures that alignment over the whole path. And that brings us to the final calculation. We just need to integrate that function from 0 to 2 pi to add up all the work over one full twist of the helix. And yeah, I know, this integral looks a little hairy, but it's just a matter of using the techniques you already know. The process is what's important. And after you work through the integration, using a little integration by parts on one term, a power-reducing identity on another, the whole thing cleans up beautifully. The total work done is 3 pi. See? Our recipe took a really complex problem and just broke it down into steps we could actually solve. All right, that helix example was pretty abstract, I'll admit. So let's bring things back down to earth, literally. Let's tackle something a little more familiar from physics, calculating the work you need to do to lift an object against the constant force of gravity. And check this out. This slide is the aha moment. On the left, we use our fancy 4-step recipe. We set up a path, do the dot product with the force of gravity, integrate, and we get negative 3 mg. Now look at the right. We use the simple formula from high school. Force, which is negative mg, times the vertical distance 3, and we get the exact same answer. That is not a coincidence. This proves that our line integral is just the superpowered, generalized version of the simple formula we started with. It works for everything. Okay, for our last example, let's look at a really special case, a situation where, as the source material puts it, the force is perfectly aligned with the motion at all times. So what does that even look like? We're going to explore this idea with a force field, F equals negative y comma x. Now, this particular field creates a vortex, kind of like water swirling down a drain, pushing everything counterclockwise. We're going to calculate the line integral around a unit circle. When your path is a closed loop like this, the answer actually gets a special name. We call it the circulation. It's a measure of how much that field wants to spin things around that loop. So we fire up our recipe again, we parameterize the unit circle, we find the velocity vector, but hang on a second. Look closely at this slide. When we evaluate the field on the curve, the vector we get is identical to the velocity vector. That is what it looks like mathematically when the force is perfectly aligned with the motion. They are the same vector. And because those two vectors are identical, the dot product becomes, well, it becomes incredibly easy. We get sine squared t plus cosine squared t, which, and I hope you remember this from trig class, is just the number 1. The thing we have to integrate couldn't be simpler. So what's the integral of 1 as we go from 0 to 2 pi? It's just 2 pi. Boom. That value represents the total push or boost the field gives to an object as it completes one full circle. So after all that, what's the big picture? The main takeaway is this. The line integral isn't just some abstract math problem. It is the fundamental tool for calculating the total effect of a changing force over a curved path. Doesn't matter if it's a swirling vortex, the constant pull of gravity, or some crazy helical journey, this one recipe can handle it all. Now, we've focused on work today, but this tool is way more versatile than not. You can use it to calculate fluid flow, the voltage difference in an electric field, so much more. So the real question to leave you with is this. Now that you have this recipe, what other complex physical interactions out there could you start to unlock and analyze?